Hello students, welcome to the class. So in the previous class, we had discussed about matter, the characteristics of matter and the ways of classifying matter. Everything we have discussed, and we had stopped at this flow chart. I'm briefing out with this and then we'll move to the next part. So matter is being classified into two ways: physical classification, chemical classification. Under physical classification, we have states of matter: solids, liquids and gases. Apart from that, we have discussed about plasma and Bose-Einstein condensate. Chemical classification, it is being classified into two types: pure substances and mixtures. Under mixtures, we have homogeneous mixtures and heterogeneous mixtures. And under pure substances, it is elements and compounds. Elements are further classified into three types: metals, non-metals, and metalloids, that is semi-metals. And compounds are being classified into two types, that is inorganic and organic compounds. Okay, moving to the next one. After completing this, we'll move to the next one, that is about the units of measurement. Before going to the measurements of this matter, we know we will discuss about different units. Before going to that, what are the properties of matter? Properties of matter, when I speak about properties, I come across two different properties of matter, that is physical properties and chemical properties. So these properties are classified into two categories. Physical properties, what are physical properties? When we say physical properties, the physical properties involve they involve, it might be color, it might be odor, it might be physical state, whether it is a solid in the form of solid, liquid or gas, its melting point, boiling point, density. So these all come under physical properties of matter. Then what is chemical properties of matter? When we speak about chemical properties of matter, what all comes under consideration are the different reactions which they undergo. A particular compound, a particular matter undergoes. It might be combustion reaction. Is it combustible or not? Or if it is undergoing combustion, is it undergoing complete combustion or incomplete combustion? Then comes the reactivity with different compounds, like reactivity with say acids or with say bases or some other compounds. Yes, metals reactivity with acids, metal reactivity with base, all these things come. So physical properties can be measured without changing the identity or composition of the substance. So if I want to say, speak about color, I will just look at the compound and I'll say the color. Odor, I'll take the smell. State, what is solid, liquid or gas. But the measurements or observations of the chemical properties, it requires a chemical change to occur. If I want to say whether a given compound, say coal, is combustible or no, I have to subject it for combustion, yes or no. Carbon, let me say, is it combustible or no? I have to subject it for combustion. So it has to undergo a chemical change. So here we come across two things: a physical change and a chemical change. So physical change is what? There is change in the state of matter only. A solid may become gas, a liquid may become gas. Yes, that is a physical change. There is change in the state of matter. Chemical change means what? Chemical change means there is entirely a new substance formed. Like for example, when I speak of mixing hydrogen and oxygen to form water, yes, so this is a chemical change wherein the two constituent particles, they have combined chemically to form a new substance. Whenever a chemical change occurs, there is formation of a new substance. Now why do I call it as a new substance? Because its properties will be entirely different as compared to these two constituent particles. Understanding? So this is about a physical and chemical properties. Chemists even describe, interpret and predict the behavior of substances on the basis of the knowledge from both physical as well as chemical properties. Okay, so we are going to learn further about the measurements, how the measurements are being done, on what basis the measurements are being done. So there we come across units, measurements of physical properties. Yes, so when we are going to do measurements, quantitative measurement of the properties is required for scientific investigation. Yes, in measurements we have quantitative and qualitative analysis we call, and quantitative analysis. See, qualitative means what? It tells us what is actually present. Suppose I'll give you a compound, I'll just say it is an organic compound. You will do certain tests to say me that the compound contains carbon, hydrogen, oxygen, let me say. Yes, this is qualitative. What is actually present? Quantitative means what? Okay, I know the organic compound contains carbon, hydrogen, and oxygen. How much amount of carbon? How much amount of oxygen? How much amount of hydrogen? That is nothing but quantitative. As the name suggests, quantity tells the amount. So quantitative measurement of the properties is required for the scientific investigation, right? So many properties of matter, it might be length, it might be area, it might be volume. They are all what? They are quantitative in nature. Okay, so there were two different systems. Earlier, two different systems were, one was English system and another was metric system. Yes, English and the metric system were being used in the different parts of the world. The metric system which originated in the France. It was more convenient as it was based on the decimal system. But today what we have, yes, today what we have is the international system of units. Before going to that, so units of measurements. When we speak about the units of measurement, we have two types of units. So fundamental units. The quantities such as mass, length, time are called fundamental quantities. They are called fundamental quantities and their units are known as fundamental units. So there are 7 basic units, students, of measurements for the quantities. The 7 basic units are length, mass, time, temperature, amount of a substance, electric current, and luminous intensity. These are the 7 basic units of measurements. The rest all, whatever comes, those are all what? Derived units. So in physics, you might have studied this very well. So we have basic units and derived units. The units which are being derived from these basic units are called derived units. Okay. So SI system. SI stands for International System of Units. It stands for International System of Units. It was established by the 11th General Conference of Weight and Measures. Yes, this is an intergovernmental treaty organization created by a diplomatic treaty known as Meter Convention, which was signed in Paris in 1875. So this SI system, it is having 7 base units. It is having how many? 7 base units. Yes, these units pertain to 7 fundamental scientific quantities. They pertain to what? They pertain to 7 fundamental scientific quantities. Other units, what other units? Can you say which are the other units? It might be speed, it might be volume, it might be density. These are all what? These are the derived units. What they are? They are the derived units. So fundamental units, basic units are how many? There are only 7 basic units. And which are those 7 basic units? The 7 basic units are, the 7 basic units are here. Here there is a table to show you all the 7 basic units. These are the 7 basic units. So which are they? You can see there. The first one is the length. Then comes mass. Then we have time, electric current. Then we have thermodynamic temperature. Next is amount of a substance. Then we have luminous intensity. Luminous intensity. So these are the 7 basic units. Now here everything is being mentioned. In these basic units, yes, if you look here, out of these 7 basic units, length, the symbol for the quantity is small l. The SI unit of length is meter, which is written as m, small m. Mass, the symbol for the quantity is m. And the unit, SI unit for mass is kg. Sorry, it is not this, it is kg. This is the symbol for SI unit. Time, small t, second. It is abbreviated as S. Then electric current, it is I. It is capital I. Okay, it is capital I. Ampere is the SI unit. It is denoted by capital A. Thermodynamic temperature, T, capital T. Small t stands for time, temperature stands for T, then capital T. SI unit is Kelvin and it is abbreviated as K. Amount of a substance denoted as small n. The SI unit is mole, MOLE, and symbol for SI unit is mole, MOL. When I want to say 10 moles, I will write 10 moles. That's it. Luminous intensity, it is the symbol for luminous intensity is IV. Its SI unit is candela which is abbreviated as CD. So here are some of the symbols, the names of the SI units and the symbols of the SI units. Yes, even you should be knowing the definitions of these basic units also. Now, let me say, if you want to speak about meter, it is length of the path traveled by light in vacuum. Definition of meter. Yeah, I'm speaking about the SI units. Length of the path traveled by light in vacuum during a time interval of 1 divided by 299792458 of a second. That much of a second. Kg, kilogram. It is the unit of mass. It is equal to the mass of international prototype of a kg. These are definitions which we should be knowing. Second. So second has got some unit definition. Kelvin has got some definition. Then ampere, then mole, then we have candela. Yes, luminance intensity in a given direction from a source which emits a monochromatic light. So we know on, and these are being present in your NCERT books also. You can have a look on it. Next, coming to the next concept, that is mass, weight, and volume. So what is mass? What is weight? What is the difference? So mass of a substance is what? It is the amount of matter present in it. Mass of a substance means, suppose if I give you an example of a block, wooden block, let me say, or wooden log, I'll give you. Yes, when I give you an example of wooden log, what is the mass of this wooden log? How much mass? 10 kg. This is the amount of substance, amount of matter present in it. Yes, and this mass is constant. You take it in across any part of the world, it remains 10 kg only. The mass of a substance can be determined accurately in the laboratory by using analytical balance. Analytical balance. What is the SI unit of mass? It is kilogram, written as kb. Then what is weight? If I say this wooden log, what is the weight of this wooden log? I still say 10 kg. So what is weight? Weight is the force exerted by gravity on an object. Weight of the object may vary from one place to another due to change in the gravity. Entire world, there is difference of gravitational force. Therefore, you go take this log to other part of the world, this log will not weigh 10 kg. So weight is what? It is force. And what is mass? It is amount of substance. So since weight is the force exerted by an object, force exerted by the gravity on an object, it will change from one place to another. It will change from one place to another. Volume. So what will be the unit for weight? We still say 10 kg. When it comes in the form of force, we use the units Newton. Yes. Then, so SI unit of mass is kilogram. Even its a fractional name is also used. If I want to say 1 kg, it is equal to 1000 grams. 1 kg is equal to 1000 grams. Grams is not written as GM, it is written as G. So 1 kg is equal to 1000 grams. It is used in the laboratories due to smaller amounts of chemicals, 1000 grams. Okay, then what is volume? Volume is the amount of space occupied by the substance. Suppose I place gases here, how much volume do they occupy? They occupy entire volume, right? So that is amount of space occupied by the matter. Its units is cubic length. Cubic length. Yes, cubic length. In SI units, volume is expressed in meter cube. So volume, since it is nothing but length, we use meter, SI. So cubic meter. We use it as cubic meters. However, a popular unit of measuring volume, particularly in liquids, is what? Liters. But it's not the SI unit, it is the common unit. What is the SI unit of volume? It is m cube, cubic meter. And here there is the the conversion factor also. 1 liter is equal to 1000 milliliters. That is equal to 1000 cc, cubic centimeter, or 1 dm cube. Volume of liquids can be measured by different devices like burettes, pipettes, cylinders, measuring plus. Now you may say, why we need all these things? We can use anyone. Measuring plus gives the exact value. Still more exact value is being given by pipette. Cylinders give us the rough value. Even test tubes we have. Yes, they all give us rough value. Burette, pipette, measuring plus, they all give us the accurate values. Yes, so it depends what type of instrument we are using to measure the volumes. We are using to measure the volumes, right? Next, temperature. Yes, coming to the next one, that is temperature. So temperature is what? To measure the temperature, it is amount of degree of hotness of a body. So there are three common scales to measure temperature. Yes, degree Celsius, Fahrenheit scale, and Kelvin scale. But out of all these, Kelvin is the SI unit. Kelvin is the SI unit of temperature. But you can even calibration of these units you should be knowing. Thermometers, if they are having Celsius scale, they are calibrated from 0 degrees Celsius to 100 degrees Celsius. Thermometers with the Fahrenheit scale are calibrated from 32 degree Fahrenheit to 212 degree Fahrenheit. If it is Kelvin scale, it is most commonly being used. It is most commonly being used. So the temp, you can have Fahrenheit can be converted to Celsius, Kelvin can be converted to Celsius, or Celsius can be converted to Kelvin, and so on. So there is the relation to convert the Fahrenheit, the Celsius into Fahrenheit, or Celsius into Kelvin. Yes, the commonly used scale is Celsius, degree Celsius scale, but the SI unit of temperature is Kelvin. And here are the two formulae. Degree Fahrenheit, if you want to convert it to degree Fahrenheit, 9 by 5 into degree Celsius scale plus 32. For example, let me say I have 10 degrees Celsius. I want to convert it to Fahrenheit. So degree Fahrenheit is equal to 9 by 5 into 10 degrees Celsius plus 32. So 5 ones are 5 twos are, so 9 twos are 18. 18 plus 32 is 50. So it is 50 degree Fahrenheit. 50 degree Fahrenheit. And even degrees Celsius can be converted to Kelvin. So if I want the same temperature in Kelvin, 10 degrees Celsius plus 273.15, sometimes it is rounded off to 273 only. So 273 plus 10 is 283 Kelvin. If I have Kelvin and I want to convert it to Celsius, so 0 Kelvin I have. So what I will do? I will go the other way around. So if I want to convert it to Celsius, so degrees Celsius, the formula is Kelvin minus 273. So what is Kelvin? 0 minus 273. So what will be the temperature? Minus 273 degrees Celsius. And this is called absolute zero. Absolute zero. This is the last temperature range. 0 Kelvin. So Kelvin scale starts from 0. Whereas, so Kelvin scale, why it is SI unit? Because Kelvin scale has got all positive values, whereas Celsius scale starts from minus 273.15 degrees Celsius. It has got negative, it has got 0 degrees Celsius, and it has got positive values. I hope this is clear. Yes? Okay. Temperature below 0 degrees Celsius, negative values, are possible in Celsius scale, but they are not possible in Kelvin scale, because Kelvin scale, the temperature starts from 0 Kelvin. Kelvin scale has got all positive temperatures. What is the temperature of human body? It is 37 degrees Celsius, or you can say 310 Kelvin, or you can say 98.6 Fahrenheit. Yes. Human body, temperature of human body, 37 degrees Celsius or 98.6 degree Fahrenheit or 310 Kelvin. Then room temperature, how we take the room temperature approximately? The room temperature is 25 degrees Celsius or 77 degree Fahrenheit or 298 Kelvin. Standard temperature is being taken. One more example, freezing point of water. Yes, 0 degrees Celsius, which comes out to 32 degree Fahrenheit or 273 degree Kelvin. 273 Kelvin. So these are the different temperature ranges. So we have three scales. Common scale is degree Celsius, but the SI unit is, it is Kelvin. Why Kelvin? Because Kelvin scale has got all positive values. Next, density. Density of a substance is amount of mass per unit volume. Let me say I have got I have got 4 blocks. Yes, okay. Okay, fine. In this, Let me say the molecules are arranged like this. What we call this arrangement? It is nothing but compact arrangement. The molecules are very close to each other. Let me say the particles are very close to each other. So interparticle distance is very less. So this is nothing but rigid molecule called atoms or solids, you can say. In this case, particles are like this. There is slight region. They are slightly free. And here it is something like this. So these are nothing but this is liquid, this is gas, and they are together called fluids. And this is solids. It is called rigid molecule, matter, right? So here, if you see, this is volume. Volume, you know, meter cube. So length into breadth into height. So they have taken 1 meter cube of volume, all of them together. Here there are large number of molecules, therefore mass becomes more. Yes, here there are less number of molecules, mass is slightly less, and here there are least molecules, mass is very less. So if the numerator is more, then the particular unit also will be more. Yes, so here, since there is large amount of number of molecules, a mass will be more. So solids are more denser, we say, most denser. They have high density. These gases are least denser. Their density is less, and in between comes gases, right? Liquids. So what is this density? Mass of a substance, mass of a substance, mass of a substance per unit volume. In the given volume, what is the mass of the substance? So mass of a substance per unit volume is called density. It is called density, mass by volume. So what is the unit for mass? It is kg. Volume is meter cube. So the SI unit of density is kg meter cube per meter cube. Usually we used to write it like this, kg per meter cube. This is not followed nowadays. We write it like this. This is the correct way of representing. Okay. The units, these units are quite very large, and chemists are often, they express the density in grams per cc, whereas mass is expressed in grams and volume is expressed in cc, cubic centimeter, grams per cubic centimeter. Okay, is that clear? Density of a substance, it tells us what? It tells us about how closely the particles are packed. If the density is more, what happens? It means the particles are more closely packed, and if the density is less, the particles are less closely packed. Coming to the next one, scientific notation. So what is the scientific notation all about? Whenever we are representing the molecules, yes, it is an exponential notation in which any number can be represented in the form, n, into 10 raised to n, where n is an exponent having positive or negative values, and capital N can vary from 1 to 10. Capital N can vary from 1 to 10. Yes, so whatever number you have been given, you have to always represent it in the form of n into 10 raised to n. Like for example, let me say I have this number 358. I have, this is not a scientific notation. How do I represent it? When we have such number, the decimal point is expected to be here. So I will represent it as 3.58 into 10 raised to. Now here the question comes, yes, or let me take one more example. Yes, so we'll represent it in the form 10 raised to n. Yes, suppose I have 232.605. Yes, I want to represent it. So decimal point is over here. Scientific notation means I should have n, and this n value should be between 1 to 9 only, not even 10, 1 to 9. Yes, you can take it as 1.00 to 9.999, anything. So I'm going to, what I'm going to do is I'm going to shift this decimal point 1 and 2 digits to the left. So what I'll write, 2.32605 into 10 raised to, how many digits I have shifted? It is to the left 2 digits. When you're shifting it to the left, you will represent positive value. When you are shifting it to the right, you will represent negative. Shifting it to the right, you will represent negative. Yes. So one more example if you want, 0.000059. I have this point. So I want to represent it in scientific notation. So what I'll do, 1, 2, 3, 4, 5, 6. I cannot write 59. It is 5 point. So 5.9. I am shifting 6 digits. Let me verify. 1, 2, 3, 4, 5, 6. So 6 digits to the right. So minus 6. I will write it as minus 6. So while performing mathematical operations on the numbers expressed in scientific notations, this was very useful. Always you have to express in scientific notation, that is n into. Yes, example. I'll take example. Addition. Let me take example of addition and subtraction. So these are mathematical operations, right? So let me say I want to add 6.65 into 10 raised to 4 and 8.93 into 10 raised to 3. Yes. So first what you need to do is when you're going to add, I'm going to remove the common factors. So for both the numbers, exponents should be same. So if I keep it 4, 6.65 into 10 raised to 4 plus, it is 10 raised to 3. I want 10 raised to 4. That means I should increase it by 1. If I want to increase the exponent by some digit, what I'm going to do is position of decimal point should be shifted to left. That is what I'll do. I'll shift this decimal point this side and it will be 0.893 into 10 raised to 4. So now both the exponents are same. Therefore, 6.65 plus 0.893 the whole into 10 raised to 4. So what do I get? I get 7.545 into 10 raised to 4. So this is addition. Similarly, during subtraction also. For example, 2.5 into 10 raised to minus 2 and 4.8 into 10 raised to minus 3. So I want to bring it to minus 2, let me say. So 2.5 into 10 raised to minus 2. This is one number. I have to subtract minus. Now see, minus 3 should be brought to minus 2. That means what you are going to add again. So yeah, are you adding or no? You are increasing the exponent. So which is the biggest number here? Minus 2. So you are going to add minus 3 plus 1 becomes minus 2. So what I need to do if I want to add, increase the exponent, what will do? Position to the left. So what it will be? 0.48 into 10 raised to minus 2. 10 raised to minus 2. So it will be 2.5 minus 0.48 into 10 raised to minus 2. And the answer would be 2.02 into 10 raised to minus 2. Understood? So if you want to increase the exponent, position of decimal point should be shifted to the left. Decrease the exponent, then position of the decimal point should be moved to right. Like for example, I have 10 raised to 4. I want to make it 10 raised to 3. What I will do? Suppose 7.8.1 into 10 raised to 4. I want to make it 10 raised to 3. What I'll do? 781 into 10 raised to 3. I'll shift the decimal point to the right. Yes. So this is addition and subtraction. Now multiplication and division. Multiplication and division. What we do? Yes, suppose let me say I have 5.6 into 10 raised to 5 and multiplied with 6.9 into 10 raised to 8. So in this case, I need not worry. Yes, I need not worry about exponents. You have studied this in maths. What I'll do directly, 5.6 into 6.9 into 10 raised to. I'll add the exponents. 5 plus 8. What is 5 plus 8? 10 raised to 13. And multiplying 5.6 to 6.9 comes out to be 38.64. 10 raised to 30. Understanding? Yes. So I need not worry. If these are in negative values also, you need not worry. Suppose 5.6 into 10 raised to minus 2 multiplied by 6.9 into 10 raised to minus 6. If it is like this, what I'll do? 5.6 into 6.9. I'll keep the same values into 10 raised to, I have to add it, minus 2 plus minus 6. So plus of minus becomes minus. So 10 minus 2 minus 6 is minus 8. And here it is 38.64 as usual into 10 raised to minus 8. Yes. Division. 2.7 into 10 raised to minus 3 I have, divided by 5.5 into 10 raised to 4. Okay. So what I will do, I will divide 2.7 divided by 5.5 into 10 raised to minus 3. 4 is going to the numerator, it becomes minus 4. So minus 3 minus 4 becomes, the value of this is 0.4909 into 10 raised to minus 7. Minus 3 minus 4. If the answer would be 2.7 into 10 raised to minus 3 divided by 5.5 into 10 raised to minus 4, then what you would do? 2.7 divided by 5.5 into 10 raised to minus 3, minus 4 goes to the numerator and becomes plus 4. So what do we get? 0.4909 into 10 raised to 1. Are you understanding? Now see, if I want to bring this into scientific notation, what I'm doing, I'm shifting the decimal point to the right. When I shift the decimal point to the right, what we will do? We will minus 1. So I can write it like this here, 4.909 into 10 raised to minus 7 is already there. Shifting decimal point to the right becomes minus 1. So what is the answer? 4.909 into 10 raised to minus 8. Minus 7 minus 1. Here also, shifting decimal point to the right. 4.909 into 10 raised to 1 is already there. Minus 1. 10 raised to 1 minus 1 becomes 0. So it is 4.909. Hope these concepts are clear. Yes. So this is about scientific notation. Yes, scientific notation. Here the same examples have been taken. You can look at the examples also. Calculations involving multiplication and division, and calculations used involving subtraction, addition and subtraction. Now, significant figures. What do we mean by significant figures? See, every experimental measurement you do, will be having some amount of uncertainty, some amount of errors into the measurements. Like for example, if I say mass of the object is 9.4 kg, if you measure it on analytical balance, it might be 9.419 or something, right? So these measurements, therefore the decimal 4 placed after the so digit 4 placed after decimal in the measurement becomes uncertain. Yes, so here we come across significant figures. The uncertainty in the experimental or calculated values is indicated by mentioning the number of significant figures. So significant figures means what? They are meaningful digits. What they are? They are meaningful digits. Here we have taken the examples. Before going to the examples, I can discuss some of the things with you all. So significant figures are the meaningful digits. Yes, meaningful digits which are known with certainty plus 1, which is estimated. So here, if we write the result, suppose of any experiment, if I write the result as 11.5 ml, say 11.5 kg. So we say that 11 is correct and 0.5, that 5 is uncertain, and it should be plus or minus the last digit. Yes, so there are certain rules to determine these significant figures. So significant figures. Significant figures. How many significant figures are there present in the given a number? Yes, that questions might be asked. So first one, what is the rule? All non-zero digits are significant. All non-zero digits. Let me say I have 5, 4, 5, 2. These are all non-zeros. There are no zero. So here in this given example, how many significant figures are there? There are 4 significant figures. Yes. Another example, say 0.25. How many significant figures are there? Non-zero. This is not significant. These are 2 are significant. So there are 2 significant figures. So this is the first rule. All non-zeros are significant. All the non-zeros are significant. Next, zeros preceding to first non-zero digit are not significant. Zeros preceding to first non-zero. So there is some first non-zero, say 0, 5, 8, 3. So zeros preceding to first non-zero. First non-zero, before that what zero comes, it is not significant. So here how many significant figures are there? There are only 3 significant figures. Yes, such 0 indicates the position of the decimal point. This question will be solved when we are using decimal point. Like for example, 0.3. How many significant figures? This is the 0 coming before a non-zero. So it is only one significant figure. These are numbers. Okay, how many significant figures? Another example, 0.05. How many significant figures? There is only one significant figure, right? One more example, 0.0067. How many significant figures? There are only two significant figures. So zeros which come before non-zero digits are significant. Next rule, the zeros between two non-zeros are significant. 205, how many significant figures? So this 0 is between two non-zeros. Therefore, there are three significant figures. 2050, how many significant figures? There are four significant figures. The zeros which come between two non-zeros or which come at the last are significant. One more example, 3.0006. So these three zeros are between the two non-zeros. So how many significant figures? 1, 2, 3, 4, 5. So there are five significant figures. Yes. Moving to the next rule. Zeros at the end or right of a number are significant, as I discussed this, provided they are on the right side. Like for example, 20650. So how many significant figures? 0 between two non-zeros is significant. At the right side is also significant. So 1, 2, 3, 4, 5. 5 significant figures. Or 0.20. How many significant figures? Two significant figures. 0.200. 200. How many significant figures? Three significant figures. But if otherwise, the terminal zeros are not significant if there is no decimal point. If there is no decimal point. So there should be decimal point, then it becomes significant. Example, very important. Please listen carefully. Let me say, yes. Hundred has only one significant figure. If I say 100.0, yes, 100.0, then there are three significant figures. Yes, such numbers are better represented in scientific notation. So how do you write 100? You write 100 into 100 as 1 into 10 raised to 2. Yes or no? We write 100 as 1 into 10 raised to 2. Therefore, there is only one significant figure. How do you write 100.10? So how do you write it? So it is shifting decimal point here. So 1.000 into 10 raised to 2. Yes or no? Yes. So therefore, there are three significant figures. There are three significant figures. Please do remember. This is the question. 100 point, decimal point is there. There is no zero. So there are three significant figures. Moving to the next rule. What does the next rule says? Continuing the numbers of objects, for example, 2 balls, 20 eggs, have infinite significant figures, as these are exact numbers and can be represented by writing infinite number of zeros placing after the decimal point. Yes. Okay. In numbers written in scientific notation, all the digits are significant. For example, if you are representing in scientific notation, 5.02 into 10 raised to 2. So it is having how many significant figures? 1, 2, 3. So it is having three significant figures. Another example, 8.625 into 10 raised to minus 3. How many significant figures? It has got four significant figures. Yes, it has got four significant figures. So these are the rules for significant figures. So based on the same rules, you can look at the example also. So addition and subtraction of significant figures. This is the example. So suppose I have 3.52, 2.3, 6.24. When I add it, I come to the answer 12.06. Yes, this 12.06, it can be rounded to 12.1. I'm sorry there, it had to be mentioned as 12.1. Yes, it can be rounded to 12.1. Rounded to 12.1. Then Adding, if I give another number, so 23.4730 is what the another number what I have given you. If I give you a different number and add it to that same number, what we do, we go for 23.47 and add it 12 point. Here there is subtraction. So when we carry out subtraction, we come to the answer of so much. We come to the answer for so much, right? So addition final, if you look at suppose addition of 3.52, 2.3 and 6.24, they have different precisions or different numbers of after the decimal point. So final result has got 2 decimal points. So it has been reported as 12.06, which can be taken as 12.0. Yes. Then if you look at the next example, I have been given you 23.4730 and I have given you two numbers, 12.11, I'm sorry. So these two numbers, when you carry out subtraction, here this is addition, this is a different answer example, this is a different example. So what do I get? I get 11.3630. So after decimal point, usually we keep two places after decimal point. So it would be 11.36. Even rounding off also comes there. When we speak about rounding off after the decimal point, suppose say 12.06 I have got. Since this is after 5, if the numbers after the decimal point, suppose you want to round off the last number, if the last number is below 5, then the last but one number, this is nth number, then n minus 1th number is kept as it is. If the nth number is 5 or more than 5, then n minus 1th number should be increased by 1. So this is 6, so I will write it as 12.1. Yes. If here, if you look at this answer, 11.36, I have rounded off. So this is 6, I will write it as 11.4. Yes. So if the nth number is 5 or below 5, if it is below 5, the n minus 1th number, this is nth number, this is n minus 1th number. I will keep it as it is. 12 point, here it is 1. I'll keep it as it is. If the nth number is 5 or more than 5, then n minus 1th number will be added by 1. Okay. Then multiplication and division. In multiplication or the division, the final result should be reported up to the same number of significant figures as present in the precise number. Okay, for example, say they have given this number 2.2120 into 0.011. So answer is this much. So you have to mention it as precise number. What is precise number? See, 0.024 is there. So this is 2. I will keep this as it is. This 3, I will keep it as it is. This 3, I will keep it as it is. So it will be 0.024. So final result after the decimal point, 3 digits. Division similarly, same concept. We'll be keeping it as it is. Yes. So this is nothing but regarding the concepts regarding significant figures, addition and subtraction or division. Yes, we have even dimensional analysis also. Often while calculating, there is need to convert the units from one system to another. Yes, that time what we do, the method used to accomplish this is factor label method or unit factor method, or you call it as dimensional analysis. So there what we do when we're doing dimensional analysis, for example, let me say, let us consider an example. So dimensional analysis. Dimensional analysis. So what is this? Where we take out which method? We take an example of a factor method. Factor method. Yes. So here factor method. So example, if you want, we can quote the example like you want to convert some of the simple converters you have. You want to convert the time hour into seconds. You want to convert inch into length. Yes. How long you want it is given in inches. You want to convert it into centimeters. You want to convert it into centimeters. That time what we go, we go for dimensional analysis factor method. Okay. So let me take some of the examples here. Examples are, let me say I have 5 inch of a piece of metal. Yes. So inch is represented like this, 5 inch. I want to convert it, that is long. I want to convert it in centimeters. So how do I convert it in centimeter? You should be knowing the conversion factor. The conversion factor is 1 inch is equal to 2.54 centimeter. Yes, 1 inch is equal to, I will mention it in a different format. So I'll write it here. 1 inch is equal to 2.54 centimeter. This is the conversion factor. Using this conversion factor, you can convert inch into centimeters. So you want 5 inch. 5 inch should be converted to centimeter. Yes, how much centimeter? So if 1 inch is 2.54 centimeters, then 5 inches how much? So 5 into 2.54. So how much you get? 5 into 2.54. So what is the answer? 5 fours are, so 5 into 2.54. So you'll get 12.7, correct? So one conversion factor I have got. What is that first conversion factor? Converting inch into centimeter. So 1 inch, IN stands for inch, it is 2.54 centimeter. This is the first conversion factor. Moving to the next conversion factor, like for example, you have liters. Say 2 liters of milk you have. You want to convert it into the SI unit, cubic meters. Yes, we know that 1 liter is equal to 1000 cubic centimeters. And we also know that 1 meter is equal to 100 centimeters. 1 meter is equal to 100 centimeters. So what it gives? It gives me like this: 1 meter divided by 100 centimeter is equal to 100 centimeter divided by 1 meter. That is nothing but conversion factor. So here I want to convert it to meters. So if 1 meter is equal to 1 liter is equal to 1000 cc. Yes, if it is equal to 1000 cc, and we know that 1 meter is 100 cc. So I have to convert it to cubic. So here also I'll do cubic, and here also I will do cubic. So 1 meter cube is 10 raised to 6. So it is, rather than writing like this, 1 meter cube is 1, 2, 3, 4, 5, 6 cm cube, correct? So this, and 1 liter is 1000 cc, cubic centimeter. So cubic centimeter I have to convert here. So what do I get? I get 2 into 1000 cc cubic centimeter into 1 meter cube divided by 100 centimeter cube. Not 100, 1, 2, 3, 4, 5, 6. 10 raised to 6 centimeter cube. So what do I get here? 2 meter cube, 1, 2, 3 zeros, and here 3 zeros go. I get divided by 10 raised to 3. So this is nothing but 2 into 10 raised to minus 3 meter cube. 10 raised to minus 3 meter cube. So this should be known to us. Coming to the another example. We'll take another example. Okay. How many seconds? See, we know that 1 day is equal to 24 hours. Correct. Then 1 hour is equal to 60 minutes. 1 minute is equal to 60 seconds. Or 1 hour is equal to 60 into 60 seconds. Yes, all these things we know. Okay, so I have to convert 2 days into seconds. 2 days into seconds. So 2 days should be converted to seconds. So 2 days into 24 hours divided by 1 day for 1 day into 60 minutes divided by 1 hour into 60 seconds divided by 1 minute. So all these things should be considered, right? So 1 hour per day, 24 hours, per minute, per hour, 60 minutes, and per minute, 60 seconds. So this calculation comes out to be 2 into 24 into 60 into 60, right? So how much answer you get? You get around 172800 seconds. This is the conversion factor. Days to seconds. You have to use this conversion factor. So why are these conversion factors required? Why are they required? For converting time, for dimensional analysis. They are required for dimensional analysis. Yes. So this is all about. Now here we have one more concept like precision and accuracy. So precision refers to what? Precision refers to the closeness of various measurements. How close the measurements are. Suppose I am doing an experiment. I have recorded 3 readings. Yes. So precision here refers to what? Closeness. How the 3 readings are close to each other. So let me say I have taken one experiment. I have done 3 sets of experiments on it, 3 steps of repetitions on it. Here I should get the answer 10. Let me say here I have got 9.5, here I have got 9.8, and here I have got 9.8, 9.9. So precision, this is not precise with these 3 values. If you look at the precision, only second and third are precise because they are very near to each other. 9.5 is 0.3 difference far, right? So precision means what? How close are the 3 repeated values to each other. Then what does accuracy means? Accuracy means how close is these out of 3 repetitions, which is the closest one. This is the closest one. So this is accurate, I say. So precision stands for how close the 3 values repetitions are to each other, and accuracy stands for the how close it is to the accurate answer. How close it is to the accurate answer. Yes, that is about precision and accuracy. Yes, precision and accuracy. So we have seen about dimensional analysis. We have discussed about precision and accuracy. Yes, apart from that, if I give you an example on precision and accuracy, you can say one of the example like, let me say here, let me say the true value. That means the result. The true value for some experiment is 2.00 grams, say. And there is a student A. What does the student do? He or she takes 2 measurements, yes, and reports the values as 1.95 grams and another value as 1.93 grams. Yes, yes. So these values are precise because they are very close to each other. Yes, they are very close to each other. So I say the values are precise, but the values are not accurate. Not accurate because the true value is 2 and it is not to the true, how close it is to the true value. Let me say there is another person, student B. He will do another set of experiment. He'll do the same experiment and he obtains the answer, say 1.94 grams. And second set of experiment, he gets 2.05 grams. So if you look at the 2 measurements, they are neither precise nor accurate. Neither precise. They are neither precise nor accurate. Why do I say they are neither precise nor accurate? So if you look at the 2 measurements, 2 experiments, one answer is 1.94, another is 2.05, very far from each other, nor the 2 values are near to the true value, that is 2. So they are neither precise nor accurate. Let me say there is another student C. He will perform experiment 2 and get the answer 2.01 as one set of experiment, one calculation reading, and second reading he gets 1.99 grams. So I can call both the readings as precise. Yes, they are precise because they are very near to each other. The 2 readings are very near to each other. And the second, if you see, they are near to the close by 0.1 difference, not even 0.1, 0.1 difference. And they are also accurate. So this is the difference. So what do you mean by precise? How close the values are to each other. Accurate means how they are close to the true value. Yes. So if you look at person A who performed the experiment, he has got 2 readings, 1.95, 1.93. They are precise, but they are not accurate. So person B, 1.94 and 2.05, neither precise nor accurate. C, 2.01 and 1.99, both precise and accurate. I'll give you one more set of experiment. You can look at the example. There are three people, A, B, and C. They have to perform an experiment getting the true value to be 10 liters. Yes, they will perform three readings. They will perform three readings. Yes, so I'll mention here true value. You are supposed to say me, are they precise or are they accurate? If it is precise, you are not supposed to say yes. I'll give you the readings. So A performs three experiments. The true value is 10 liters, as I said. So here the A value gets 9.3, 9.4, 9.33. Okay. Second person performs 9.2, 9.5, 9.7. And the third person performs the value 9.99, 10.01, and 10.02. Yes. So look at this and tell me, are they precise? So here there is so let me make it in the form of tabular column. Okay. I've got these lines here. Yes, so I have a tabular column here. Okay, so let us see 9.3, 9.4, and 9.33. Yes, they are precise. But are they accurate? When you speak about accuracy, it is 9.33. You have to consider it to the true value, and it is very far, so it is not accurate. It is not accurate. Coming to the next one, 9.2, 9.5, 9.7. They are not precise because the values are very far from each other. Are they accurate? Look at the true value. Is it 10 somewhere? No. So they are not accurate. Yes. Then 9.9, 10.01, and 10.02. Are they precise? Yes, they are precise. What about accuracy? Yes, they are also accurate. So precise means how the three values are related to each other. Are they very close to each other? Closeness of the three values, 3 or 5, whatever a type of number of experiments or set of readings you have taken. If there are only 2 readings, you will consider 2 readings. How the readings are close to each other. Accuracy refers to how they are near to the true value. So accuracy means what? How they are close to the true value. True value. Precision means what? How they are close to each other. How they are close to each other. So precise, there's hairline difference. So precision and accuracy. So this is very important in doing the calculations, right? Very important. Okay. So this is about precision and accuracy. So we have seen about significant figures. We have seen about scientific notation. I have given the examples also. You can see here the scientific notation, exponential form, n into 10 raised to n. So calculations example here, you can look at the example 5.7 into 10 raised to 6 into 4.2. When you are doing multiplication, the exponential values are not brought to common one. They are just added up. When you're doing division, they are subtracted. If it is 3, it becomes, when it goes to the numerator, it becomes -3. If it is -3 here, when it goes to the numerator, it becomes +3. During addition or subtraction, first these two operations, the first numbers are written in such a way that they have same exponent. Here it is 3, here it is 2. It should be brought to same exponent. Whether it get it to 2 or you get it to 3, doesn't make a difference, but exponential value should be same. Yes. Later, when you get the final answer, students, remember, try to convert it to the scientific notation if it is not there. See, this is already present in scientific notation. I need not worry. This is not present in scientific notations. What I need to do? 2.394 into 10 raised to 11 is already there. I am shifting the decimal point to the left, so +1. So it is 2.394 into 10 raised to 12. Here there is no problem. Here 48.22, shifting to the left, it becomes 4.822 into 10 raised to 3. Here it is 4.2 into 10 raised to -3, not a difficulty. When I am shifting to the left, positive value. When I am shifting to the right, negative value. +1, +2, how many decimal points you have shifted, it will become positive, that much positive. And how much you are shifting to the right, it becomes negative. And apart from that, we have discussed about significant figures also. I hope all the rules are being clear to you. Then we have seen about dimensional analysis, that is using the unit factor method. Conversion factors are there. You can use those conversion factors to convert meters into centimeters. You can, sometimes they are given in derived units, but you want them in SI units. That time also we can go for the same. Yes, days can be converted to hours, days can be converted to minutes, days can be converted to seconds also. All the units can be converted, interconverted from one unit to other. In the next class, we'll be discussing with the further part, that is laws of chemical combinations. Very important laws. There are around 5 laws which govern the entire chemistry. Yes, very important laws that we'll be discussing in the next video. Hope you have understood this. Thank you.